So I'm Nathaniel Boggs, and I'll be presenting our work on a new framework for measuring defense in depth that we've developed. You may have some deja vu, and you saw me yesterday, where I was talking about our work on drive-by download defense in depth, our SPICE framework. And this was this key idea of linking attacks to be able to, across layers, to measure defense in depth and total coverage. Our work was focused on this methodology to measure the detection rate and looking at collecting real data in the wild. Today, we present our framework called Wind Tunnel, which builds on this idea of linking across layers to measure defense in depth, applying this to web application and attack vector, but more generally, tackling three additional crucial issues that present themselves when we try to actually measure defense in depth and measure in general, that being generating synthetic data sets that are realistic and useful, measuring the false positive rates, not just the detection rate. As we know, cost, especially cost of false positives, is a huge issue in this measurement to see how you design your security architectures, and then end-to-end automation with a modular framework so that you can plug in new controls and test them very easily, or new data sets and whatnot. So now I'll talk a little bit about the motivation behind this work, and then describe the system architecture of Wind Tunnel, and then I'll talk a little bit about some of the example experiments that we did to show what kind of capabilities you can do with this framework, the results of those, and then I'll conclude with some future work and concluding thoughts. So the motivation here is to answer these simple but crucial questions, such as, are we secure? How can we be secure? What is it going to cost? What do we need to do? Whom do we need to be secure against, and how do we represent those? I put forth that there are four critical variables in trying to answer and address these questions, that being time. Everything evolves over time. What organization, putting this in an organizational context, each organization will have different normal, attacker capabilities, what security controls, and by this we're using security control to find anything that can detect or prevent an attack, whether this is your antivirus, your network sensor, your host sensors, users, whatever controls in a very broad sense here, typically deployed in defense in depth so we can measure those together. So talking about time, the attacker capabilities always evolve and change. Security controls themselves evolve and change, either based on the data over time or new detection capabilities. So any framework, any approach that we want to do to test this has to be easily expandable and repeatable. If you just do something at one time that doesn't scale, that you can't repeat over time as new technologies evolve, it's not going to be useful. With organizations, there's some set of normal, some set of costs. Different organizations treat false positives in different manners. They have different cost structures. So everything we need to be able to measure false positives, the costs, and we need to be able to configure what normal looks like to be able to generate different numbers for what may be different data sets, different organizations. We have to be able to represent attacker capabilities. So we have a large variance. You might be worried about somebody who just has access to existing scripts versus nation states, and everything in between. So we have to be able to represent different attacker data and be able to plug that into a framework, and be able to have the granularity to be able to say, well, for a particular set of attackers, you're going to have these results versus another set of attack data, and so on and so forth. Security controls deployed in defense in depth. We need to, be able to test these attack vectors. Hopefully we can test those separately and combine the results. We need to be able to test these against many layers, so we can't just test one security control in isolation. That's going to give you a very skewed view, because in reality you're layering all these controls together. Most of the time, oftentimes they're not independent, so we need to be able to measure is total coverage, total detection rate of some set of security controls, which may be detecting attacks based on very different looking data. So I'll give you an overview of our system Wind Tunnel. So this is a modular framework and implementation of an end-to-end approach measure the web application attack vector. So this means we go from generating the normal data, the attack data, testing, collecting at different layers, testing the security controls that exist at each of these layers, parsing those results, putting them together and presenting them in whatever graphical or data format you want. So the keys to this is automating this whole process to make it easier to repeat experiments, to test new pieces of experiments, whether that's new types of normal data, attack data, evasions, different web applications, different security controls to be able to ease that cost. So here's a visual representation where you can see, we take some existing user content as a seed to a Selenium client that can drive a full-fledged web browser, can use cases to interact with a web server. And when it does, we collect that data in multiple layers at the network layer, database layer, host layer, collecting system call information. Do the same thing then with attacks. So we take some set of exploits, some set of evasions, permute all of those so we have each combination of those. Use the Metasploit framework to do this, and then to launch these attacks, to exfiltrate, do some activity on the web server, exfiltrate some data, for instance. Collect all that, labeling this data, and then testing it against various security controls at different layers, being able to aggregate those results. So as most people are familiar, there's advantages and disadvantages to real data, synthetic data sets. Real data can be realistic, but it's hard to share because of privacy concerns. It's hard to collect. Attack data may be very sparse, especially with higher-end attackers. Synthetic data, it's easy to share. You can repeat experiments, but it's hard to make it realistic. It's hard to tell you representative attacks, but ground truth, which can be very critical, you have more control over when you generate the data yourself. So in this work, we're using synthetic data, and we're trying to improve on existing synthetic data sets in 3 particular ways. And that is, we want to collect it at multiple layers, so not just a data set of network packets. We want to collect the network traffic that went with these database calls, that went with these system calls. And you could imagine expanding that to additional layers. We want a modular design in that we can change some variable in the generation of the normal data set. So instead of just having a one-time, okay, everybody get together and we'll make this one perfect data set, well, time moves on, right? We want to make it modular so we can change some variable and regenerate the data set to test different hypotheses and such. And also make it so that it's easy to plug in and say, well, here's this new web application that behaves very differently. Let's generate data for that. Let's add some use cases and be able to generate that data more easily without having to redo a whole experimental system. And then being able to regenerate this data on the fly allows us the possibility of doing inline testing. So if certain security controls interact with the data in some way that you can't use them offline, you can apply those and be able to retest those inline and replay very similar data sets back to back and test different controls that way. So some of our sources for public data, so we want to reuse real user content, maybe a little out of place, but you can imagine if one of your use cases is post a new blog post to WordPress, well, what English text do I put in that blog post? Well, maybe I can use some data from a scrape of Usenet, Wikipedia, Stack Overflow, these existing data sets of English text. And then for usernames and passwords, we use other instances of real data in the wild. To actually drive this normal data generation, we use the Selenium framework, which allows you to drive a full-fledged Firefox browser and emulate users clicking on different objects and interacting with the website. So we generate, some gigabytes per hour worth of network traffic using this. We test 3. We set up right now in our existing framework. We have 3 web applications fully implemented with WordPress, DikiWiki, and TestLink. But the modularity, the goal is that you can relatively easily add additional ones and design additional use cases. For our attack data generation here, we use the Metasploit framework. So we have some exploits for each web server, and then we have some evasion, such as padding attacks to evade anomaly detectors, HP level, for example, base 64 encoding. And then this is, the whole key here is that this is easily expandable. So if you have a new evasion that you want to test, then you just need to find that evasion as a Metasploit module, and then add that into the script that permutes those, and then you don't have to redo your data generation. You don't have to find new sensors. You can test that evasion technique with an existing end-to-end system. And then we label these based on the attack window because we know exactly when the attack's happening. We know where the attack's coming from. We can then gather our ground truth data there. So our main security controls that we test, that we have integrated into our framework right now, are generally content anomaly detectors. So we use various previous work and implement these models on top of Stand, which is an automated sanitization framework that deals with the training phase and takes care of the training automatically for us, and gives us a nice platform to integrate to add individual different models that build a model of normal on the set of content, and then detect attacks by looking for abnormalities in the data set going forward. So for instance, for the web, there's a set of anomaly detectors that are attribute-based that parse the user submitted content from a web request. So for a GET request that's after the question mark here, they parse out each attribute, so they have a different model for what is user supposed to look like typically, what does password look like typically. The other one, so anagram and spectrogram, would take that entire string and look at that in different approaches. So we deploy these different security controls across layers. So we deploy, so each of the anomaly detectors builds a model on the content for the different layers. And then in addition, we deploy Green SQL, which is a signature-based detector for SQL injection attacks. And we deploy a probabilistic anomaly detector for file access pattern attacks, abnormalities, and a system call sequence sensor on the system call layer for the host layer there as well. And then again, the whole point of this is to be very expandable. So to add a new sensor, you set up that sensor, and then you have access to all the data, and you send it in the same alert format, and everything will work nicely. So for our experiments, we wanted to show some of the capabilities of our framework. So the idea is you can change, the input to normal. You want to, this is synthetic data set, so you want to know what different configuration parameters will influence the results. So for instance, we want to see just what the natural variation is. So if we just repeat the experiment and generate new data sets or generate them for different hardware, is there any significant variation there? We want to vary maybe the source. So instead of using the Wikipedia English text, we use the Usenet scrape or Stack Overflow. Does that affect the different sensors, the false positive rates and detection, and so on and so forth? And then, we vary the application. We do more drastic things to go from WordPress to TestLink, and that probably has more influence. And then we compare to a baseline real data set from a production web server. So here's a visualization. So we take some baseline data set, and then we have different experiments where we repeat that on different machines. We vary the content source. We vary the length of, so if you make a blog post, what if it was half the length? Or what if it was always twice the length? How much would that affect it? And then change the application. So here, for time, I can only go through some highlights here of our experimental results. But so looking at the experiment with varying the content source. So here we have a graph of the cumulative distribution function of the normal score. So this means that on the y-axis you have the percentage of of scores that were less than or equal to that amount. So on the x-axis, you have the actual score. So for instance, if you can see that almost 90% of the scores for most of these have less than a score of 5, where a higher anomaly score for this particular sensor means that it's much more abnormal. So in here we have the 3 different lines represent the different data sets used. So this is this is the attribute character distribution sensor looking at the web layer on 3 different data sets. One, the red being the Usenet scrape, English text being seeded, versus the Wikipedia text being seeded versus the Stack Overflow text being seeded. And you can see here, for the most part, a couple of them are about the same, and then Stack Overflow, we have this, 3 to 5% of these normal scores that were much higher for this particular sensor. And this is probably likely because the Stack Overflow probably has a wider variety of characters as they're pasting and talking about code instead of just more typical English text data. So this is one visualization that you can see how changing the normal, so for different environments, might affect your output, for instance. And then varying applications. So here, this is a much larger graph where we have, on the left, you have each of the security controls. On the top, you have each of the data sets. And in each cell, you have the area under the curve. So this is the area under the ROC curve, where you graph the false positives versus the true positives. So as you get closer to the 1, that means that you've detected everything and no false positives. So a higher number is better here. And this is a nice metric in that you can look at it in one number. It has some flaws in that it doesn't account for the raw number of false positives. For instance, you could imagine we have a lot more system calls than we do web requests. So a 1% false positive rate on system calls, you might be talking about in the thousands or tens of thousands, whereas on web requests, maybe you're talking about hundreds. So by itself, this metric may not be the best to compare between sensors that are operating at different layers, but between data sets, it can be an interesting, easy metric to look at to compare how different sensors perform differently on different data sets. So we have, for instance, looking at the right side here, we have our WordPress baseline data set, and then we are comparing it to the TikiWiki and the test link on the far right here. You can see there's some general variation. For instance, we have one fairly drastic change where our anomaly detector looking at the attribute existence fails completely on the TikiWiki data set, and that's because it's working on a fairly simplistic model where it's just checking to see whether this request has attributes that it has seen before in the normal data. So it's not the best sensor, but here you can see it as an example of what types of things you can do, and you can see some more finer variation. On the far left, you can also see where the CUCS data set is a production data set that we collected on our department web server. So you can see some comparison there. That's the type of thing that the type of data you can generate with this kind of framework. So comparing our synthetic data sets to real production data set. So for instance, we can plot another cumulative distribution function. So we can take one sensor and plot it against different data sets, how it performed against different ones. So in this case, we looked at the web layer anagram anomaly detector. And you can see, the normal scores have fairly different distributions here based on the data set. So it's heavily influenced by what normal looks like. In particular, you can see the CUS data set has a large number of normal requests that have at or close to 100 anomaly score, which you can see very clearly influenced on the ROC curve on the right, where the false positive rate is similarly significantly higher in that data set. But this is the type of thing that you can generate automatically, or you can have some data sets and some set of sensors and choose them and be able to generate these types of things to be able to do that. So now, as you saw yesterday, we can draw these concentric circles where we have each arc represents a single attack, and we can plot all the different permuted attacks. So then each individual circle represents a different security control. So for instance, the outside circle represents the web layer with using the anagram anomaly detector algorithm. And each one that's green is where you've detected the attack, and each one that's red is where you've missed the attack. And the key thing that we can do now that we have, yesterday we just had this detected or not. But now where we're looking at, well, detected at some false positive rate because we have normal data available to us. So this is for a 1% false positive rate against this baseline data set. And the same as before, you can see how the different sensors compare. And if you had some set of sensors, you could compute, the total coverage, the total detection rate of those series of sensors at some false positive rate. So for instance, we could, what if we're more strict and we need a 0.1% false positive rate? Then you can generate that. Or 5%, and you have these drastic changes in detection rate that you can easily visualize. And then maybe percentage, the false positive rate maybe isn't what you care about. Maybe your cost is based on the raw count. So for instance, if you have to look at each individual alert, maybe you really care more about the number of false positives per day or per data set per time period rather than the rate, because the rate won't tell you how much maybe you're actually, it's actually going to cost you. So maybe you change it and you can see, it affects different sensors very differently. You can vary the rate. You could imagine that you might even weight the different layers or the different sensors. A false positive at the web layer is going to cost me X amount to look into or man hours versus one at the host layer. Maybe I have different parsing or some other factors that might influence the cost there. But that's the type of thing that we can generate while you're looking at it in terms of defense in depth as a whole with multiple layers and being able to compare those. So in conclusion, in future work, we have this framework. We've done these experiments. We've set up, 3 web servers with a handful of attacks with, 19 different security controls operating at these layers. So really, the value comes in this type of framework when it's expanded to more attacks, more evasions, more different types of normal data. So we're most certainly looking for collaborators who are interested in using this approach to, maybe you have a new sensor that you want to test against other sensors. Maybe you want to test different variations in normal data. So in conclusion, we present this modular framework that allows you to experiment with variations in normal data, replay this data, generate new data sets much more easily. We can compare between different layers. The goals here, we can share and repeat experiments. You can more easily benchmark new sensors. And this whole idea is reduce this cost of testing and be able to expand and be able to measure defense in depth in more detail. So if you have any questions, and then the data sets we used are currently available. They're rather large, and we're packaging the framework itself in a more distributed format with virtual machines. Hopefully that will be able to, images we'll be able to distribute in the near future for you to actually use, and feel free to contact us with any questions. Thank you.
Thank you, our speaker.
So you seem, you definitely have a pretty cool environment there, but I was wondering if you keep adding, more and more and more, as you had in your previous slide, isn't that going to be a bit kind of overwhelming to just figure out, okay, now I have all that, and what do I really do? So what's the right strategy to just, you know, to really take the gist out of it and to really benefit from what you have? I mean, because you could generate thousands and thousands of graphs and then so what, right? So what is the strategic direction, so to speak, that you want to take with that environment, which is really cool?
Sure. So I think the key is the data is very hard, right? So, but once you invested in taking a lot of time and a lot of effort and coming up with, you know, significantly advanced attacks and evasions, and, you know, depending on what sensors you're using, you need to model different aspects of the normal data. So, for instance, I brushed over it here, but in the paper you can see where, you know, we had to choose certain attributes of normal data to relax, right? For instance, so we didn't model like fine-grained timing of user interactions with the web server. But if you have a sensor that needs that, you can add that in. So I think going forward, it'd be really focus on the data, because once you have really good data, then your results are actually hopefully predictive of real-world scenarios. And then testing the sensors that people are actually using or care about. So maybe some of the sensors that are strictly worse, you don't graph them very often. You know, you might still run the test, but if it's strictly worse than another sensor, or, you know, subsume, then maybe you don't even look at it. And you can probably automate that. And you can, instead of graphing all the sensors, you only look at, you say, well, this organization already has some set of sensors, so you graph those, and then you graph the ones that give you a better marginal detection rate, for instance, or something. But yeah, I think the data and the visualization of how you actually process the results is very important. It's wide open. It's very important, and there hasn't been a lot of work done in the area, and I think it's really wide open.
Questions? One. So your idea for evaluating against different types of attacker is to list evasion techniques. And it seems to me that the problem with that is what we have seen in the return-oriented programming community, that if you list evasion techniques, you know, A, B, and C, and build your defense based on that and evaluate it against that, attackers would come up with, or researchers would come up with, you know, simple evasions, D, E, F, that you haven't thought of. And, you know, for anything other than script kiddies, the numbers wouldn't hold up. How would you evaluate against attackers that are anything more sophisticated than script kiddies?
Sure. So part of it, I think, is there's some limitation in a purely empirical, let me have some data set of attacks and test it. So there's other ways of looking at the problem and measuring. You can look at what's the cost to the attacker to bypass this particular evasion, for instance. So you could reason about it that way. If you do want to look at it in a strictly empirical, let me test sense, then I think you have to, you know, come up with a new control. And people are pretty good about that. If you read people's papers, you know, they'll list, here's the types of evasions that we suspect going forward. I think it's one of the time things, right? So once you have a new security control, you can't just test it before it's even used. You have to test it in the future and say, well, what are the evasion techniques for this one? And add those in. So you add that in as another evasion technique, and then you see, and maybe this sensor, because it works on other things, it's useful, or maybe this new evasion it just adds another hole, for instance. But I think that's the time thing where you really have to iterate more and more.
Is there any other question? All right, so let's thank our speaker again.